Hello everyone, this is a presentation of our final project, cat sound analysis using deep neural networks. Today, we'll guide you through our project in the following order. Does anyone here own a cat? Cats express a wide range of emotions and needs through their voices. The goal of our project is to develop a high accuracy model that can automatically recognize these cat sounds and classify their meanings. To achieve this goal, we based our work on this paper. This paper addresses the challenge of achieving high classification accuracy despite the scarcity of cat sound data, which is very difficult to collect. We decided to develop our own model with this paper as our primary reference. The dataset we used was provided by the paper's author. It contains MP3 audio files, each labeled with 1 of 10 distinct emotional states. This paper proposed a unique technique called FDAP, which stands for Frequency Division Average Pooling. It's a modified version of a conventional global average pooling. With FDAP, the feature map is divided into low and high frequency bands, and then average pooling is applied to each band individually. So, why is FDAP so effective for analyzing cat sounds? As you can see on the left, cat sounds are frequency varying data. FDAP is effective because it can properly segment and capture features from these multiple frequency bands, leading to a better classification performance. After feature extraction, the paper used 5 different classifiers and assembled it, and use these evaluation metrics. Refer to the slide for further details. Now, let's break down the overall process of the reference paper. The paper's methodology consists of these 5 main steps. First, in the pre-processing stage, audio samples with an average duration of about 4 seconds are adjusted to a uniform length of 29 seconds using zero padding or clipping. Next, a Fourier transform is applied to preserve time domain information. Finally, the audio is converted to a Mel spectrogram, serves as an input to the CNN. Next is data augmentation. To address the issue of the limited data, the paper used several methods. These helps the model learn from the more diverse sets of sound patterns. Because collecting a large amount of cat sound data is difficult, the paper utilized transfer learning to address this scarcity. It uses a CNN pre-trained on a million song dataset, which is a large-scale collection of audio features. This is where FDAP is applied during feature extraction. Features are extracted to layer 1 to 5 of the CNN. The FDAP method divides this layer into 1, 1, 4, 4, and 3 segments respectively. Each of the 13 segments produce a 1 by 32 feature vector, and these are concatenated to form a single 416-dimensional feature vector. The vector is then fed into 5 classifiers, and the final prediction is made through an ensemble vote based on the outputs of these classifiers, and n-fold cross-validation was used. Here are the key results from the paper. The table on the left shows that the ensemble model achieved the highest accuracy of 90.8%. Accuracy increased from just 70.71% with the original data and global average pooling to 90.8% with 3 times augmentation and FDAP. From these results, we learned several key things. First, using FDAP in the CNN led to an average prediction accuracy increase. Second, data augmentation significantly boosts performance. Finally, the success of using million-song dataset for transfer learning showed that features from one domain like music can be effectively applied to another sound classification. Now, let's discuss our team's approach. We implemented a structure similar to the original paper but introduced modification to differentiate our work, particularly in the transfer learning pipeline. We adopted the PANS library as our new transfer learning source, and here is the reason why. We selected CNN14 because this model is more closely resembles the structure used in the original paper. At each step of the process, we followed a slightly different approach from the paper. For pre-processing, we use librosa library instead of Capre. Unlike the paper, which set the audio length to 29 seconds, we set it to 5 seconds considering the average length of our dataset is 4 seconds and audio set clips are longer. For data augmentation, we apply one of the 5 augmentation methods randomly to each sample. So our final dataset is expected to differ from the one used in the paper, but the final number of the samples are the same as the paper. As mentioned, we perform transfer learning using CNN14 as a feature extractor. Unlike the paper, which likely perform fine-tuning, we use the pre-trained model as is without additional tuning. This results in a much higher dimensional feature vector. The paper used a fixed size of 416 dimensions, while we retained the original output channel size of CNN14, resulting in a 5,312 dimensional feature. However, the pooling methods and FDEP implementation are the same. To prevent overfitting, we use K-fold to ensure that original samples and their augmented versions were not split across the training and test sets, which ensures a more honest evaluation. You can see our accuracy, F1 score, and AUC all improve with more data augmentation at the table below. Here is the direct comparison with the paper. With one-time data augmentation, our model achieved an accuracy of 83%, while the paper reported 86%. With 3 times our data augmentation, our model achieved 89% accuracy, which is very comparable to the paper's 90%. As a practical test, we applied our classifier to the meowing sound from a teammate's cats. We recorded a mother call and the model successfully classified it correctly. In conclusion, although we followed a similar structure, there were several differences in our implementation that led to some variations. Our approach achieves a strong performance by simply using CNN14 as a feature extractor without the need for additional fine-tuning. As a result, while we did not fully surpass the paper in terms of accuracy, we developed a model that achieved comparable performance. Just as the paper demonstrated the effectiveness of MSD, we found that using audio set also has a positive impact on the cat sound classification model. That concludes our presentation. Thank you for listening.